what we were talking about last time was being able to formulate this analysis problem in a more mathematical way. And we were talking about how this, if you have a structure given geometry, loading, and all the material properties, the job of analysis is to try to find out the displacement field. The displacement field as a function of x, where x can be any point in the domain, right? And we talked about that if you, the essential equation that we are trying to solve to find out the displacement field was to solve the equation of equilibrium. And I gave you this example. By the way, all these slides or quote-unquote handouts are already posted on the Blackboard, and I'll keep posting them regular intervals. So yeah, hopefully all of you know that and keep checking up on that. So this was the example that I gave you about if the displacement of a unit cube is given to be x, then the final shape after deformation it just becomes 2x, right? All right, so then we took a look. We started to take a look at this cube. How many of you actually downloaded this handout and have it with you? Very few, okay. So let me talk a little more in detail about this cube. So what we are talking about here was that, let's say we have this structure, we apply the load, and it deforms to this new configuration. So we said that we want to enforce equilibrium in the deformed configuration. So in order to enforce equilibrium, I'm going to consider a small rigid body around my point. And that small cube around my point, I'm going to zoom it up and try to denote what are all the forces that are acting on my rigid body. Right, so this is a finite sized rigid body right now. The dimensions are delta x, delta y, and delta z. But after we figure out all the forces that are acting on this rigid body, we are going to take the limit when delta x, delta y, delta z tend to 0, and then try to see what equations we come up with. And so I'm not going to set this problem a little in the last lecture, so I'm not going to go into too much detail. But a couple of things I'll point out here. So one thing here that we used was how to figure out what are all these stresses or tractions that are acting on these faces. So this is a small infinitesimal cube. And if you go to the midpoint of each face, then you can find out tractions. Tractions and stresses, there's a little bit of a difference. So how many of you have not heard of the difference between the traction and stresses? Okay, so this is also something that you might have seen in a solid mechanics class, perhaps in your undergraduate. The stresses are denoted with this sigma, and the traction is a physical quantity that is similar to pressure. Okay, so let's say you have a surface, and you attach some sort of a glue, and you try to pull that entire surface, not necessarily normal to the surface, but in some tangential, some direction that is normal to the surface, and it has some tangential component. So that physical quantity is a distributed force per unit area, okay, and that is called traction. And traction is related to stress with this relationship. This is called the Cauchy relationship. And once again, I need to point out here is that this Cauchy stress is the real stress, okay? You might have heard about other measures of stresses, Pila-Kirchhoff and whatnot. The only real stress is the Cauchy stress because it is related to equilibrium, okay? So whenever you're talking about equilibrium, you talk about Cauchy stress in the deformed configuration. All right. So after that, all that you have to do is to try to figure out what are these tractions that are acting on all these faces. And then we just have to sum up all the forces in the x, sum of forces in the y, and sum of forces in the z. And those are our equilibrium equations. And in addition to that, we needed to do this Taylor series expansion that I was telling you about last time as well. So take a look at this. This is the sigma xx on the first face, which is related to the sigma xx on the second face, and by how much does it change in going from the second face. So this is the second face in the back here. In the middle point, there is sigma xx2. Going from this middle point on the back face to the middle point of the first face, the change is delta x. So using a Taylor series expansion, we can express this relationship, and we are going to neglect the higher order terms. There are no terms with delta y and delta z because there is only change in x going from 2 to 1. Okay? So you set up these three equations and you plug them into your equation of equilibrium, where we are saying that some of the forces in the x direction. So let me just give you example of one of these terms. So this is this term sigma xx1, which is the traction that is acting at this point. So this is your face 1. Sigma xx1 is this thick red line, and this is the traction that is acting normal to this face at this point. So if I take this traction, and I just told you that traction is a force per unit area. So if I take that traction and multiply it with this area, I will get the total force that is acting on this face in the x direction, right? So the area of this face is nothing but delta y times delta z. So what we are doing is we take sigma xx1 times delta y times delta z. On the opposite face, we have the opposite sigma xx on the face 2, the same delta y delta z. And once you plug in all these relationships into this equation, what you get is this first equation right here. And this equation is nothing but what you might have seen in mechanics as div s plus b, right? So another point here that I like to make is, now if you are not familiar with tensor notation or indicial notation, you can use any notation you want. But really, it's up to you and to see that, if you don't use indicial notation, if you don't use tensor notation, you will have to write out three equations. A short way of writing the same three equations is using this. So just plug in the values of I and j. I and j are just indices that denote x, y, or 1, 2, 3, and so on. And this equation is where the index j is summed up from 1 to 3. So for a particular value of I, let's say I is equal to 1 or I is equal to x, if you plug that in here, what you're going to get is this first equation right here. If you plug the value of I is equal to 2, you get the second equation. If you plug the value I is equal to 3, you get the third equation. And note that I'm saying that plug only the value of I, not necessarily the value of j, because the value of j is being summed up. So this entire equation, I could replace j with any other number. I could say k, it wouldn't matter, right? The important thing is that the value of I denotes one component of the vector equation. So people realized this, and what they did was they started to write this equation in a further shorthand notation. And that shorthand notation, you omit this summation sign, and you assume that when the reader will look at this j and j, which is a repeated index, the reader will interpret this as being a sum on j. Okay? So if you do that, and you also denote this derivative, so this derivative is denoted by a comma j. So del of del xj is just denoted as comma j. So this is a further shorthand notation about how to write all these three equations in just single shorthand notation. Okay? So this is just notation. If you don't understand this notation, you are welcome to use all the expanded notation. Okay? All right, so this was one notation, and in yet another notation, we write this quantity is a divergence of stress, where stress is a tensor. And another note about things, I'm going to denote tensors with a under tilde and vectors with a underline. Okay, so so this equation right here can be expressed in a coordinate free form. What does that mean? Somebody might say that my xyz are here. Somebody else might come along and say that, well, my xyz are here and oriented in some other direction. This equation does not depend upon what xyz you choose. Okay, so that's the benefit of that. And obviously, the equation of equilibrium does not care what xyz you choose. It is a fundamental physical thing, right? So this equation and the three equations that I showed you above here, they are both coordinate dependent equations. But this equation, this is a vector slash tensor equation. It does not depend upon what coordinate you choose. So for example, in the homework problem 2 that I gave you a cylindrical wedge, a cylindrical infinitesimal cube. That infinitesimal cube is very similar to this infinitesimal cube, but you have to be a little more careful when you are summing up the forces. Okay? So in the cylindrical coordinates, you will see that the equation that you get for equilibrium is this exact one. And I'm going to omit, in the homework, I didn't ask you to calculate this. But if you remember from dynamics long back, the equation for acceleration in dynamics has some other terms. So I asked you to derive only the left-hand side of the equation, which is the static part. Okay? And you'll see that the divergence, the definition of divergence just changes a little bit in the cylindrical coordinates. All right, so now that I've introduced this, uh, going back to this mathematical model, we had this thing, and now we know how to solve for ux. But try to imagine this. So if we tried, this is an equation that must hold at each and every point in the body, right? How do we even come up with a function of x, u as a function of x, that will satisfy this partial differential equation at each and every point of this body? And that's what this course is all about. Okay. So let me ask you this. We know we just proved that in order for equilibrium to hold in the deformed configuration, the equation that that we need to solve for at each and every point in this deformed configuration is div s, or div sigma plus b is equal to rho u double dot. Does that equation hold anywhere outside? Obviously, the real structures are supported on real soil, right? So let's say you go to some point in the support. What do you think? Does that equation hold there also? It's an equilibrium equation. So if the structure is resting on something that is not a rigid support, the equilibrium equation must hold at that point also, right? And that's huge. What that means is you choose any point, anywhere, anytime. Okay, this equation right here is a statement that says momentum must be conserved in a point-wise manner at each point, anywhere in the universe, at all times. Right? That's huge. That's the premise of Newtonian mechanics. These are things that Newton said 400 years ago. And obviously, more recently in the 1900s, people were not able to refute his claims. But early in the 19th century, people found out about quantum mechanics, that when you go really, really down to the scale of atoms and all that stuff, then Newton's laws start to break down. And then Einstein found that if you go to really long scales, then general theory of relativity comes in, which and again Newton's laws they start to break down. But at our scale, at the scale of structures, at all the things that we do, all we study is if you want to look at it that way, all we do is try to apply Newton's laws to all our structures. All right. So that's a little bit of a context of how important even mechanics is. So, but here I've also introduced to you a little bit of a notation about vectors and tensors. So let me talk a little more about that. And I'm going to ask you to take notes along with me here. So before we get to talking about tensors, we all know what a scalar is, right? Scalar is a physical quantity that we can represent with just one number. And it has just one magnitude. Example, temperature. And related to a scalar is a scalar field. So what is a scalar field? What do we mean by a scalar field? Anybody? It's okay, yeah. I'm sure your answer is going to be right. Okay. So let's say you have a body, and if you're measuring the temperature at each and every point of the body, then all the temperature as a function of x, that's a field, right? So let's say temperature is T, and let's say this again is your body, the same beam. I promised myself that I'm not going to draw any potatoes in this class. So this is my body, and if I measure temperature at all these different points and express them as a function of x, that is a temperature or a temperature field, a scalar field. Okay. So how about a vector? We know that it has magnitude and direction, and in 3 dimensions we can denote a vector with 3 numbers. And similar to a scalar field, we also have something called a vector field. Can anybody give me an example of a vector field? Okay, example of a vector first. Velocity. Okay. And obviously, if you try to measure the flow in a pipe or a flow in some sort of a body, then each and every point in that pipe or each and every point will have its own velocity. Or this entire body need not have the same velocity, right? So velocity is an example of a scalar, and velocity field if you measure it at different points in the domain. So V vector as a function of position x. So this is a vector field, and note here that T is, I'm not drawing an underline under the T because this is a scalar function of a vector variable. This is a vector function of a vector variable. Okay. So that brings us, well, before I jump into tensors, let me ask you, so let's say we have this vector that's maybe pointing in this horizontal direction. Okay. And let me call this vector V, and I'm going to say that this is my coordinate axis, E1, E2, E3. So how can I represent, and let's say the magnitude of this vector, this V, is denoted by capital V. So how can I represent this how do I represent this vector V in these coordinate systems? It is equal to V, the magnitude of this vector, times the unit vector in this direction. So that unit vector right here is E1. So this is the definition of that vector, right? And if I write it out in components, I can write it out as v, 0, 0. So this is after the choice of, after I choose a coordinate system, I can express my vector as a 3 cross 1 matrix. So this is not really a vector. This is a 3 cross 1 matrix. But some other guy comes and says that, well, my coordinate system is going to be oriented like this. So E3 prime, E1 prime, E2 prime. So what is the definition of this vector in this coordinate system? Minus V times E prime 2. So minus V times E prime 2. And if I express that in the coordinate systems, it becomes 0, minus V, 0. So as you can see that if I try to express my vector as a 3 cross 1 matrix, the definition changes from coordinate system to coordinate system. And therefore, a vector is a physical quantity which is coordinate independent. Okay? After you choose a coordinate system, you have to, your individual components of the vectors will change. And the reason I'm telling you this is that it's related to tensors. So ideally what I should do is attach 0, or this is the origin O there, and this is origin O prime, O, E1, E2, E3. This is the coordinate system that I'm denoting. So in this coordinate system, I can represent my vector V as this. If I do not specify the coordinate system, then that definition of a vector is not complete. Okay. Similarly, I can say that E1 prime, E2 prime, E3 prime. This is the definition in the other coordinate system. And now I can say that both of these definitions are equivalent. Okay. So, and finally, there is also a concept of a vector space. So, how many of you have heard of a vector space before? Okay, a few of you. And so a vector space has a little more technical mathematical definition, but what we are going to, for our purposes, we are going to say that a vector space is a set of all possible vectors. So for example, in 3 dimensions, there's the example is the real 3-dimensional space, R3. The set of all possible values or all possible vectors, if you arrange 3 numbers, that entire set is the vector space. So what we essentially are saying is that every vector in this real world is a part of a vector space. Okay, and I was going to show you this, the more precise mathematical definition of a vector space. This is a link from this website, which is good for referring for reference about mathematical things. This is Wolfram Math World, World of Mathematics. Anybody seen this website before? Okay, few of you have used this. So this is a good website, a little more technical than Wikipedia, but more or less the information here is good quality. And these are the same guys who make Mathematica. Okay, so the important thing that I want to point out here is that any vector will have certain properties. That's the way we define what a vector is. So a vector is a quantity that follows these laws, these 7 laws. A vector has to be commutative, associative, it has to have an additive inverse, it has to have the additive identity, additive inverse, associativity, distributivity, and another distributivity. All right. Apparently there's an 8th equation also. So this is the multiplicative identity. So if you come up with some quantity that satisfies all these 8 laws, then you can call it a vector. And that does not necessarily mean that it has to be a 3 cross 1 matrix. It can be anything. And by the way, if I'm going too fast for you, I'll be uploading the video for this lecture and all the previous 2 lectures also and all that. So you can go back home and take a look at this at your own pace, which will hopefully help you in case you're not able to follow my accent or if you're having other difficulties. Okay. So, all right. So getting back to the lecture. Now that we know what a vector space is, what vectors are, what scalars are, what is a tensor? Who can tell me what a tensor is? I'm sure you guys talked about this last time in 570 for those of you who took it. So what is a tensor? Anyone? Anyone remember what the definition is? Yeah. It is related to a matrix, yes. Okay, so that's a good example. So what I'll do is, I'll say that I'll give you an example of a tensor first, and then I'll tell you what the definition is. It's a little bit of a roundabout way, which I find is a little easier to understand. So let me give you the example. Example sigma, the Cauchy stress that we were talking about all this while, right? The Cauchy stress is a tensor, and we can represent that Cauchy stress in a matrix form, 3 cross 3 matrix form. But there's a little bit of a difference with a matrix and a tensor, which is not that important, but except if you're a mathematician. So okay, so here's the definition of a tensor. A tensor is, let me actually move this down a little bit. A tensor is a quantity that operates on a vector and produces another vector. What do you think? This is a ridiculously simple definition, right? And it doesn't even sound technical enough. So the first time when I took a look at this definition, I said, what is this definition? A tensor is something that takes an apple and turns it into an orange. Right? It doesn't sound that technical enough. All right. So what the more mathematically correct definition is that a tensor is a linear map from one vector space to another. So what we are essentially saying is the same thing, that a tensor is going to take or operate upon a vector to produce another vector. It is a map from one vector space to another vector space. But this is just a little more quote-unquote technical way of saying the same thing. But the definition of the tensor is exactly right here. It takes a vector, operates upon it, produces another vector. Now, I just gave you an example of this tensor, that is the Cauchy stress. So can you tell me which are the 2 vectors that are associated with this Cauchy stress? What vector does Cauchy stress act upon to produce what vector? The position, so the Cauchy stress is a function of position, but it doesn't actually act upon the position. Right, right. So the normal vector n, that is the vector that Cauchy stress acts upon, right? So if you go back and take a look at this thing that we were talking about right here, this is the Cauchy relationship. If you take the Cauchy stress and if you apply it or operate upon this n vector, what you are going to get is a traction vector. It takes the normal vector operates upon that and gets the traction vector. And if you don't remember this relationship, this is something that you again must have seen long back in solid mechanics when you draw that tetrahedron and you try to do the balance of forces. That just helps you figure out what is the traction on an inclined face. Okay. All right. So that's the example of a tensor, and how is it related to a matrix? So we know that we can express this Cauchy stress as sigma xx, sigma xy, sigma xz, and so on. But the only difference between a matrix and a tensor is again the same difference that we had in terms of vectors. If you choose one coordinate system, you get one set of components. If you choose another coordinate system, you get another set of components for a vector. The exact same thing happens in a tensor. If you choose one set of coordinate axes, you are going to get one set of components, 9 components. You choose another set of coordinate axes, and you are going to get a different set of 9 components. And do you guys remember the Mohr's circle? Right? So if I draw this small rectangle in 2 dimensions, I will have stresses that are acting in these directions. And now if I rotate my coordinate axis, let's say by 45 degrees, I'm going to get a different set of stresses. And the relationship between all these different sets of stresses was our Mohr's circle. So if you draw that Mohr's circle, let's say these are the 2 principal values, sigma 1, sigma 2. This is my Mohr's circle. And if you change the angle by theta here, you draw a line like this. Let's say this is the first set, and you draw another line like this. This is the second slope. So this is the first plane. This is the second plane. The state of stress can be obtained from this Mohr's circle by using this sort of a construction. Okay, so hopefully this should be familiar to you. But there's a much more elegant way of doing the same thing. So that concept is coordinate transformation, and hopefully again you are all familiar with this, perhaps not in this particular way, but what I'm trying to do here is, let's say I have this vector v. I have one set of coordinate axis e1, e2, e3, and I have another set of coordinate axis e with a prime there, right? So how do I convert from one set of coordinate axis to another set of coordinate, to components in another set of coordinate axis? So as you can see here, I've expressed my vector v first in this coordinate system. So I'm saying that v is equal to vi ei. And you should also note that I'm using the summation convention here. My index I is repeated. So I'm saying that vi ei is actually equal to v1 e1 plus v2 e2, v3 e3. And that's what the definition of the full vector would be if I follow the summation convention. Okay, and in components I can represent the same vector like this. I'll get some number v1, v2, v3. These are 3 scalars. Now if I want to change to a different coordinate system, this coordinate system, then my components in this new coordinate system are going to be different, v1 prime, v2 prime, and so on. How do I find out v1 prime, v2 prime, v3 prime if I know v1, v2, and v3? That's the process of coordinate transformation, right? So one easy way to do that is you express both vectors on the left and the right hand side, and you dot that equation with a unit vector from the new coordinate axis, right? So all I'm doing here is I'm saying that vi prime ei prime is equal to vi ei. So v is equal to v. That's all I've done here, and I'm post multiplying this equation with ei prime. I'm taking a dot product. So if you remember, the dot product of two unit vectors, ei, ej, that's just delta ij. Delta ij has the values 0 and 1, and you can represent delta ij as this identity matrix. So if you take an identity matrix, multiply it with a vector, you are going to get the same vector. And on the right hand side, what you have is ei dotted with ej prime. So what does that mean? That is a product. Let's say, for example, you have E1 and you dot it with E1 prime. So if you have E1, this vector dotted with this vector, that's not going to be 0 or 1. It's going to be some number from -1 to +1, right? So that number goes into this matrix. And now this matrix is also a 3 cross 3 matrix, but this is not a tensor, okay? This is a coordinate transformation matrix, okay? All right, so that's a little bit about the how to do coordinate transformation, what are tensors, what are matrices, and so on. So I'm sure I'm going pretty fast here, but I sort of want to push on the gas a little bit because, you know, we have a long weekend coming up. Go back and take a look at the handout and take a look at the lecture. If you have, try to do the homework. If you have any questions, post it to the forum, and I'll be checking on that forum pretty frequently. So in the 5 minutes that I still have, let me just briefly talk about this vector products. I'm sure you've already seen the dot product before, and just so that you get familiar with the indicial notation, I'm writing the dot product in indicial notation and the vector notation. So if I have two vectors u and v, and if I want to dot them, all I do is multiply their components together and sum up, right? And that can be represented as matrix multiplication. So you have a horizontal 3 cross 1 vector, vertical 3 cross 1 vector. If you do a matrix multiply, you get the dot product. Similar thing for cross product. If you calculate the determinant of this matrix, that is your cross product. And in the indicial notation, you can express this cross product in this way. Again, the summation convention applies over I, j, and k, because I is repeated, I occurs here and occurs here, j is repeated here and here, k is repeated here and here. So this is the formula in terms of indicial notation. And if you don't understand indicial notation, write it all out and see whether this is indeed what you get or not, okay? And finally, there is this new type of product that you might not have seen before if you didn't take mechanics. This is called the tensor product. So you can also construct a tensor from two vectors by using what is called the tensor product. And if you were to write it out in terms of matrices, you can interpret this as the first vector in a vertical column, the second vector in a horizontal column. And if you do this matrix multiplication, what you will get is this 3 cross 3 matrix. Okay, so this is also called sometimes the outer product of two vectors, which is nothing but the tensor product. And note again that I'm saying that this is not equal to, this matrix is not equal to the tensor. It is, this tensor can be represented in a matrix form if you choose a certain coordinate system, okay? So the important property about this tensor product is, again, going back to the same thing. A tensor is a quantity that acts on a vector to produce another vector. So if I take the tensor T, it acts upon this vector X. What is the vector that it produces? That's the question that I'm asking. So you have this tensor, that's T, acting upon X. What it produces is, you take these two vectors and dot it. And put that dot here, and I can put that dot here because after a dot product, the result would be a scalar, right? So this is a scalar multiplying one vector. So that's your tensor acting on a vector to give you another vector. And in the matrix form, this you can see this more simple in a more simple way. You had this original U cross V or U tensor product with V. That's right here, U tensor product with V. If that tensor were to act upon a vector, the easier way to calculate is that dot V and X. And when you dot this, this will become a scalar. That scalar goes here. What you're left with is this vector. Okay. So this is how tensor product operates upon a vector. So there's a whole section on kinematics. I just have barely enough time to introduce to you this. So the reason that I'm going back to this kinematics is going back to the problem that we were trying to solve. We have this structure, we have loading, we have geometry, material properties. How do we find out Ux? And we said that the equation that we are going to solve is this div sigma plus b is equal to 0. But I mean, if we solve this equation, the u, our unknown variable displacement, doesn't even occur in this equation. So we need two other relationships. The first thing that we need is, we know that our stress is going to be related to strain. That's the material model, right? Because if we solve this equation, we know that we can express stress in terms of strain. And we also know further that we can express strain in terms of displacement. So if you plug this equation here and this equation here, then this equation becomes an equation in terms of u, which you will be able to solve using the techniques of mechanics or finite elements, as we will talk about later. But the important thing is that we still need these two relationships. So let's take a look at this relationship. How is strain related to displacement? Okay. And the very first or the last time I was telling you about this relationship, that if you are given the original configuration and you represent any point in the original configuration with this big vector x, and any point in the new configuration with this small vector x, the relationship is that this small x is equal to the big X, which is this vector, plus this vector. And another way of saying the same thing is that small x, this small x, is a function of big X, and that function is called the deformation map. So how many of you remember studying this deformation map from last time? Okay. So yeah, this is the same deformation map. And the reason we are studying this deformation map is because we will be able to express displacements and strains in terms of this deformation map. So just to remind you, strains, if you remember, were change in length over original length, right? That was our sort of undergraduate definition of strain, delta L over L. But obviously in 3 dimensions, strain is much more involved. And the important thing here is to notice that the strain is actually related to the changes in deformation. And what I mean by changes is taking a derivative. So the most important derivative of this deformation map is deformation gradient, F. And that is a tensor. And all that we are doing is taking the derivative of dx, d small x over d big X. And essentially, you can try to interpret this as something that takes, again, this is a tensor, it will take a vector to another vector, right? So take any vector. So this is my undeformed configuration. Go to a point, draw a small, very small infinitesimal sphere around it. And if you mark all these small dx vectors, then F is going to act upon it, and it is going to produce an ellipsoid. So this is very important. In entire continuum mechanics, the only mode of deformation is that if you go to a point, draw your small set of vectors, the only possibility is that it will deform into an ellipsoid. There are no other modes of deformation because F is linear, F is a matrix. And as you know that if you express F as a form of a matrix, it will have some eigenvalues, and those eigenvalues are actually stresses that act, stretches that are acting in these principal directions. But what I'll do is I'll stop here, and on Monday or actually next Wednesday, take a look at this lecture. And if you are struggling with all these concepts, go and take a look at the sections in the book that I've already marked in the handout. And I'll upload this maybe in a couple of hours. And if you have any questions, just let me know. Okay? Just take a look at this. We'll go over it more slowly in the next lecture, and we'll also finish out this theory of elasticity that we're talking about. Okay? All right. See you guys Wednesday.